Uh, uh, can you hear me?
Yes, sir. You can hear me.
And the screen is visible, right? My screen.
Yes, here is visible, sir.
Yeah, so it's already 6.
Uh, Happy teacher to you, sir.
Arre, thank you, same to you.
Yeah, learning from you, sir.
So, yeah, shall we wait for like couple of minutes and then we'll start?
That will be good. That will be better, I think, sir. So that
Yeah, yeah. Okay, then we'll start
can again.
around 6:05.
Right, sir. Yeah.
Okay, okay. Okay, so I think we can start. Uh, Basically, today I have changed my notes app because this by default app it's there in the iPad, but it was not giving the whole PDFs. Uh, if you had seen the notes that I've shared with NPTL team for a couple of last weeks, last pages are missing. So anyway, I have changed the app. I hope this is also good only. Uh, I tried it sometimes and it's better. So anyway, we'll start with the discussion of the topic. So first of all, uh, what is fluid mechanics or any uh, if you have heard this term mechanics anywhere, mm, Yeah, so basically, whenever there is mechanics like fluid mechanics, solid mechanics, or any other continuum, I don't know, but yeah, fluid mechanics, solid mechanics. So wherever this mechanics term is there, you are basically studying the quantities which don't have any mass. For example, in fluid kinematics, if you have noticed, it involves typically the study of quantities such as velocity, acceleration, vorticity, uh, then some stream functions, potential functions. So in any of those, if you check their units, you will never find uh, mass unit in them, because this is a branch of science which deals with quantities that are not directly dependent on the inertia of the body under observation. So in solid mechanics also, if you purely consider solid mechanics, there also you will not consider the mass effects of the body on parameters like velocity, acceleration. And here also in fluid mechanics, you don't consider mass effects. Like, I mean, you consider or you study only those quantities or those flow parameters which are independent of mass. So that is the first thing that should be clear, what is fluid kinematics. And then, uh, yeah, before doing anything else, we should know, uh, like, I have seen this in class notes also, and it is actually the first thing that is taught when somebody teaches you fluid kinematics. So, like, there are, uh, I'll draw here two approaches to study fluid motion. One is called as uh, Lagrangian approach. Another is called as Eulerian approach or Eulerian approach. So this is the first thing that you should be familiarized with when you even start to study this topic. So can somebody tell me what is the difference between these two?
Sir, Illyrian is like it is position wise per position. Lagrangian is continuous, continuum.
No, that is not, because both these approaches are continuum based approaches. Uh,
But
so
if you take measurement at one particular place, that becomes Eulerian approach. And
yeah,
if it continuously, some like it is a particle wise, every particle will consider imaginary, so that becomes Lagrangian.
yeah. So basically, uh, uh, yeah, what you are saying is also partly correct, but just to refine on it, uh, in Lagrangian approach, you basically define your velocity or acceleration of the fluid flow for a particular particle. So it is a study of the fluid flow is done on a single fluid particle by defining its position vectors with respect to some reference point. So study of fluid flow with respect to position of fluid particles. So basically, you take a particle in the fluid domain and you trace its path with respect to time, and then you, based on the velocity, based on the this thing, based on the curve that particle follows, you define the velocity as well as acceleration with respect to some reference. Whereas in Eulerian approach, you basically fix your uh, you know uh, area or the volume of analysis in the fluid domain, and then you only consider the particles entering that area of observation and leaving that area of observation. So here you fix your uh, here fluid motion is studied by fixing the space of observation, and other, like, you fix your space of observation and then you define other field variables with respect to that. So here for any particle, its position, so this position is the s is the variable that I'm using to define the position of the particle, and it will be a vector and it will be a function of its initial position and the time. And then you define velocity as a rate of change of this position with respect to time, and then acceleration as rate of change of velocity with respect to time. I am representing the vector quantities with the horizontal line on top of that variable here. Later we will drop this because it will become cumbersome. And here what you do, here you define uh, your velocity as a function of x, y, z and time. So, and similarly acceleration also you define some function x, y, z and time. So basically your acceleration becomes, or your velocity and acceleration or any field variable becomes function of space and time. Whereas in Lagrangian approach, it is primarily a function of time. So then, so basically, we follow Eulerian approach in fluid mechanics because, uh, as you know, in the fluid domain, there can be a lot of particles. The number can be very high, very huge, and therefore it is not at all convenient to study each and every particle and then study the whole domain. It is cumbersome, but more than that, it is not practical. Nobody will be able to do that uh, in a feasible manner. Therefore, Eulerian approach is the way to go, or the way that we follow here in the fluid mechanics course. So this is the basis of it, and then
Sir, sir, I understand, sir, in Lagrangian approach, like one particular fluid is followed, like we study that the travel of a particle basically throughout its journey. But in
yeah,
case of Eulerian approach, particular is not followed. The position is like whatever particles come from a particular position, they in that position only study its properties. Is it not?
yeah. So in Lagrangian, you follow the particle. In Eulerian, you don't follow the particle. If the particle comes under your space of observation, then only you study, and you study the particle properties within that space only. If it leaves, then it's okay. Uh, Let it go.
So,
You don't care.
sir, it is basically control volume approach, Eulerian approach. Is it not?
Yeah, you can understand that way, uh, because there we have RTT, right, Reynolds transport theorem, which is the link between control mass and uh, control volume. So here also you can draw the analogy, but yeah, you should know what it is. I think what you are implying is also intuitionally correct only, but yeah, this is the exact definition that I've written here. But yeah, what you are saying also can be a good way to remember this. Okay, so
Yes.
then yeah, then there is this thing to connect these two. For example, there can be some acceleration for the fluid particle or the fluid domain in Lagrangian approach, and there can be acceleration in the Eulerian approach, but they can be, are they same or not, how to connect them. So there the derivation is given in the class. So basically we have a total derivative which is again comes from the Lagrangian. So this is the total acceleration. So yeah, it is the total acceleration of the fluid particle or fluid domain, and then you use something called as uh, Eulerian, this thing, Eulerian description. You get uh, I think it is V only, not Del again. So yeah, so this is the link between these two. So this is called as total derivative, and this is acceleration because that is the most important parameter in this whole study. This is called as local or temporal component, and this is called as convective or advective, or sometimes it is called as spatial component also. So you should know these terms because in some questions they only mention that it's a local acceleration. Then if you don't know what local means, then you'll be stuck again. So you should know that. Uh, yeah, and if somebody doesn't know what this ulta triangle, inverted triangle means, it's a gradient operator, and there is a dot between velocity vector and the gradient operator that represents the divergence. Uh, so I hope you are familiarized with these mathematical operators. Then yeah, so this will be basically your total acceleration, and yeah, so if the flow is steady, this del v by del t term goes to 0, and if it is uniform, so when I say uniform, that means the flow is independent of the space through which it is observed, or the spatial coordinates. It is not a function of x, y, z basically. Then the convective or the spatial component of the acceleration will go to 0. So that is happening in uniform flow. So maybe I'll just write it here only as a side note, which can be useful later. So this will be 0 for steady flow, and this will be 0 for uniform flow. So that is there. Again, mm, yeah, then one second before moving away from this, there was one thing which I wanted to highlight here only. So basically, there are like three coordinate systems in this course. Since it's a introductory course, we primarily study Cartesian coordinate system. So Cartesian coordinate system means there are three axes perpendicular to each other, and we represent them by XYZ coordinate system. But there are other two coordinate systems also. One is called as a polar or cylindrical coordinate system, in which there will be r, theta, z. So r will be the radial coordinate, theta will be the angular, and z will be the perpendicular to the r theta plane. And then there is third coordinate system, which is called as spherical coordinate system, in which you will have r, theta, psi. So r will be again the radial component of the coordinate system. Theta is the angle made with one of the planes, and psi will be the perpendicular angle to that plane. So, but I think for this course, what I've seen mostly, uh, you are Cartesian coordinate system is the important thing that you should know, but some you should know that there exist more than that. So there are like polar coordinate systems and spherical coordinate system, maybe not part of this course, but they are there. So anyway, yeah, so before moving on, again, there is one more important concept here, which is called as path line, streak line, and streamline. So, as the name suggests, path line is the curve that is, you know, developed by tracing the path of the single fluid particle at different time intervals. So it is basically what you do in the Lagrangian approach, because in Lagrangian approach you follow the particle and you trace its path, and that is how path line is there. Uh, that is what path line is also defined as. Then there is something called as streak line. It is not, I mean, for some domains it is very important, but for majority streak lines are not studied in that depth. But you should know what is streak line. Streak line is, for example, if you have a nozzle, so the nozzle end from which fluid is coming out, that that is considered as the starting point. And what you do at at any time interval after that, you trace all the points that have left the tip of the nozzle and where they are at that point. So it is again like streak line is, it is instantaneous picture of all the particles that had passed through the nozzle tip. So that is what streak line is. And streamline, we will talk about it in more detail, but again, streamline is uh, okay. I'll spend more time on streamline, but the other two definitions should be clear. And since we don't have enough time here to discuss those things, what I did this time is uh, one second. Yeah, so I have copied these links. So if you are interested in seeing, uh, what are, like, how to solve uh, any problem based on, you know path line, streak line, streamline, uh, you can do that. Let me just see if I can paste that link here. There should be option of pasting, right? So link is here. It is also like one of the, why am I not able to paste it? One second. Oh. Anyway, so there are other, like, I came across a couple of good NPTEL classes. I'll put those links here maybe later, because right now I'm not able to paste them here for some reason. I don't know why. If I do that, yeah. So now I'm getting the option of, yes. So I got the uh, so one link. Oh, this is too small actually. One second. Mm, yeah, maybe I'll increase the size to, let's say, 20. Now it is okay. So I'm giving you like couple of links here. You can go back maybe after class or sometime later, and you can watch these two. I think these are like 20 minutes lecture. I can obviously tell you here, but then we don't have enough time remaining. So that's why I'm not focusing on it right now. But if you are interested in understanding the concept of path line, streak line, I think these are very good resources. You can go through them. Hey, come on. Hmm. Okay, so now we'll spend more time on streamlines because streamline is the one that is important uh, concept that as far as our course discussion here is concerned. So, first of all, the equation of streamline or what it is. So, by definition, it is an imaginary line. It's not a real line. So, I'll put it here only because this is also a very important question. It is asked in many, uh, you know, 1 second. No, I'll just put, sorry. Uh, yeah, so imaginary, it's not a real thing. And it is, uh, so like like it changes with respect to time, so at any instant of time it can be it can have some other shape, and after some time it will have some other shape. It is not a fixed thing, uh, fixed line or fixed curve, and uh, it is imaginary line or curve, and by definition if you draw a tangent to the streamline, you will get the velocity at that point at that instant. And I saw like very tedious formula which is used to remember the streamlines, but I will give you one simple formula that is actually very easy to remember. So this is the equation of any streamline. Dx by u equal to dy by v equal to dz by w. What is uvw? So if you have a velocity vector, u is the x direction component, and w is k direction, v is the j direction. So if you remember this box formula, uh, your life will be very easy. So uh, typically, what I've seen that some people remember this as dy by dx is equal to v by u. So okay, but when you don't like after some time you will forget and then it causes confusion. Anyway, so you can remember this way, and yeah, there are some properties of streamline that should be known to you.
So then, what is the difference between stick line and streamline? Because they look to be same.
Okay, I understand this doubt should be there because I have not spent much time on these concepts. But again, we have time constraint. But coming back to your point, streamline is the line that I talked about, the different property that when you draw tangent to it at any point, it will give you the velocity at that point in that time. But streak line is, again, go back to the example, or maybe you can check this YouTube links later. These are again from NPTEL course. I don't know which one, but I just came across them. So streak line is nothing but if you have a nozzle, I'm explaining again. So if consider the nozzle tip as your starting point, and at t equal to 0, there is no fluid coming out from there. But at let's say t equal to 1 second, some fluid is coming out. Then at t equal to 2 seconds, some additional fluid came out. So what you do, you at any instant of time, you go back to initial point and you connect all the particles that came out from the nozzle tip, and the locus of all those points is a streak line. It's not easy, or it's not easy to picture it. That I understand because when first time I studied, I also did not get much of it. But it is my request to you that just go to this two YouTube links. You will understand it much better because it has like there they explain with the animations and all, so that will be a better reference. So we like in the interest of time, I have to cut short on that part, but it's there. You do one thing, you just check these YouTube links out, and maybe next time in next class, if you don't understand from these links, maybe you can ask me again. Anyway, I start 10-15 minutes earlier. We can discuss at that time also. But right now, come back to the streamline. So yeah, the streamline equation is there, but more important that like uh, two streamlines or even even single streamline never intersect each other. So what I mean is, if there are two streamlines in a fluid domain, they will never intersect each other, because what happens if they intersect, there will be a point of intersection, right? And at that point of intersection, if you draw two tangents from two streamlines, one point will have two velocities, which is not true. That is not a physically possible thing. So therefore, streamlines never intersect, and one streamline cannot intersect itself also. For example, if there is a streamline going like, let's say like this, and if it comes back and intersect itself, this is also not possible, because this point will have two velocities at that point. So that is what I meant by this point. It is very important point. And there is no flow across a streamline. So flow will always take place between two streamlines. It will never cross streamline perpendicularly, and therefore solid surface can also be considered as a streamline. I think this was one question asked in one of the competitive exam. Like one of the option was solid surface. So because I'm like, typically there is like, if the surface is solid and it is not penetrable or porous, there cannot be any flow across that surface, and therefore that is also a streamline. So uh, yeah, and the last thing, uh, for steady flow, uh, path line, streak line, and streamline coincide with each other. So these lines will be separate only in the unsteady flow. If it is a steady flow, then uh, it doesn't matter. All these three lines will be same only. So before going to the next topic, what I would like to do is, maybe uh, we will solve one simple problem. So question is, uh, velocity field is given as 5x cube I cap minus 15x square y j cap, and okay, I should not write and, because, and it is asked that find equation of the streamline. So again, I'll just go back to the formula. So here only I and j components are there, which are x and y components. The z component is not there. So here the equation of streamline is given by, general formula is dx by u dy by v. So here u is 5x cube, here u is 5x cube, and v is minus 15x square y. Therefore dx by u is 5x cube equal to dy by minus 15x square y. So x square will get cancelled, 5 3 cancel, therefore dx by x will be equal to dy by minus 3y. So then you can solve this. So you can take minus 1 by 3 outside and you can integrate on the both sides. So here you will get ln x. Here minus 1 by 3 will come out. This will be ln y. And there will be a constant of integration, let's say ln c. Then you can, eliminate ln x. So I can take it as ln y power minus 1 by 3 plus ln c. And therefore, this becomes x equal to c into y power minus 1 by 3. Or maybe we can write it in a simple form, which is x y cube equal to c. I have taken that, oh, sorry, I did a mistake here. So basically, it becomes x equal to c by y power 1 by 3. Therefore, x y power 1 by 3 is equal to c. This is the, one second. Yeah, so this is the equation of your streamline. So this is how you solve such problems. Okay, then we'll move to the next topic. Forgive me if I'm doing things in a hurry, but to be honest with you, it is very difficult to cover everything important in fluid kinematics in uh, limited period of time. So what I'm trying to do here is cover the important concepts initially, and maybe in the end, if we have some time, we will solve some interesting problems. And therefore, I'm slightly going at faster pace as compared to usual thing. So after that, there is important topic of continuity equation, or mass conservation, also they called mass conservation equation. So you should remember that for any physically possible flow field, it needs to obey the conservation of mass, or the continuity equation, and that is useful in many cases. So like, I'll just write a general equation of conservation of mass. If you remember, in the RTT also we did this only, that we took beta equal to 1, and then it become volume integral of rho d volume plus surface integral of rho v dA equal to 0. And similarly, if you do, like, if you draw that analogy, and there is a derivation about this also, but I'm not going into that. I'll just give you a general equation. So there is a unsteady term here. Then there is this is your spatial terms. Rho is nothing but the density of the domain, fluid in the domain, and this is the general equation. It is valid for all compressible plus incompressible steady plus unsteady, because we have a time dependent term, right? If it is steady, this del rho by del t will go to 0. And again, uniform, non-uniform. And also viscous or non-viscous or inviscid typically. So it is valid for all type of flows, because it is a general mass conservation equation. And then what you do, maybe I'll just give the derivation. It is not that difficult. So what you do, you apply chain rule for this rho u, rho v, rho w terms, and then you expand. So what you get? Del rho by del t plus u into del u by del rho by del x plus rho into del u by del x. So this is the second term. So this term is just nothing but the chain rule for the second term in the general equation. Similarly, again, if you do, it will become rho by del y plus rho del v by del y. Again, this is your second term in the previous equation. Similarly, there will be third term. So nothing fancy. I'm just I'm just using the chain rule of this thing, what you call differentiation, and writing the terms. Now you rearrange them, and how you rearrange them? This del rho by del t remains as it is, and then there are these terms u del rho by del x plus v del rho by del y plus w del rho by del z. And then what you do, you take the rho common out of the remaining three, then you get del u by del x, del v by del y, del w by del z. This is just rearranging of terms. And now if you see this quantity here, this is nothing but divergence, which is nothing but the, or maybe I'll write capital V, divergence of the velocity. And then this term, these three terms is nothing but the this operator into rho, and this is nothing but rho is there. So therefore uh, you have final form of the equation, which is del rho by del t plus uh, this this term into rho, plus rho into equal to 0. Don't worry, this is just uh, this thing, what you say, simple derivation comes out of it at the end. And as we seen earlier, this is the total derivative that we talk about. So this is nothing but capital del rho by del t, and it is equal to 0 because this is the mass balance. So this term goes to 0. Uh, 1 second. Oh, I should not say that way. That is wrong. This is just a total derivative term with respect to density, and the second term is as it is. So now this term goes to 0 for incompressible flow, as we have seen in previous classes also. So therefore, uh, for incompressible flows, or maybe I'll just write arrow. So this implies your divergence of velocity field will be 0 for incompressible flow. So from here only we get the very famous equation, which is del u by del x plus del v by del y plus del w by del z equal to 0 for incompressible flows. Okay, and it is valid for uh, steady as well as plus unsteady flows. So people typically sometimes confuse these with the steady and steady. It doesn't matter because we are considering total derivative equal to 0, which is capital D rho by capital Del T. So this is very important equation. It is used in almost all the problems that you can think of. I will take one small example here just to make you familiarize with this. So yeah, uh, there is a velocity field which is given as lambda xy cube minus x square y I cap, and then xy square minus 3 by 4 into y power 4. This is your j cap, and it is asked that find lambda for incompressible flow. So now to solve this question, we know uh, the convention that I am following. This is your u component of the velocity field, and this becomes your v component. So if the flow is incompressible, we have this divergence of velocity equal to 0, which is del u by del x plus del v by del y equal to 0. So this is the condition that we need to satisfy in order to make the flow incompressible. Now, and it is a 2D flow, so there is no del w by del z. So now what is del u by del x? Now you basically differentiate lambda xy cube minus x square y with respect to only x. So I am assuming that everybody knows what is del, like partial derivative with respect to something. So when you take partial like not partial, I should not say partial, let's say derivative, if there is a function of two variables x and y, and if you take derivative only with respect to x, then you consider y as a constant and then you differentiate, and vice versa. So here we are differentiating a function of two variables which is in the bracket and only with respect to x. So therefore we consider y as a constant and do the differentiation. So then first term lambda is also constant, y cube is also constant with respect to x, and del x by del x is equal to 1 minus y remains constant and x square differentiation is 2x. So we get lambda y cube minus 2xy as our first term, and del v by del y is again del by del y of xy square minus 3 by 4 into y power 4. This is your v, and therefore del v by del y. So here again x will be constant, so x into 2y minus 3 by 4 is constant, and this becomes 4y cube. So this becomes 2xy minus 3y cube, and therefore the summation of this two quantities should be 0. This is your first quantity plus 2xy minus 3y cube equal to 0. So this 2xy gets nullified with each other. Therefore, lambda minus 3y cube equal to 0. And we know that y cannot be 0 for all cases. Therefore, lambda minus 3 has to 0, and therefore lambda is 3. So this is your solution. So this is just a simple case study of applying continuity equation for a fluid field. Any doubt here? Or it's clear? Okay, I think nobody is asking, so no doubt. So anyway,
we'll see again. Okay, we'll see again, sir, the note actually. You'll understand it.
okay.
Yeah.
Maybe you saw these notes later, and maybe if you have any doubt, next class we can again come back to it.
Yes, sir. Yeah.
Yeah, and before moving to the next point of discussion, yeah. So this is like this formula, which is I'm like squaring it right now. This formula is oh, like valid for Cartesian system, but if you have a polar coordinate system, this is just an additional thing. If you don't understand, that is also fine. But if you are preparing for GATE or some competitive exam, it's better to know. So in cylindrical or polar coordinate system, actually, for many days I did not know cylindrical and polar coordinate system are same. I knew cylindrical coordinate system, but this polar coordinate system was a new word for me. So anyway, just a personal thing. So in this case, the continuity equations remain this same only, but since your xyz is now replaced with r, theta, and z, this it takes the form of this type of form, del by del of r into vr plus again 1 by r del by del theta of v theta plus del vz by del z equal to 0. So because of the change in the coordinate system, uh, this like dangerous looking form it takes, but it's not that dangerous. You need to just maybe if you are interested, you can go through the derivation. It is available in any standard book, but if not, then you can just remember this way also. It is fine. This is just additional thing. I don't think for this course we need this, but just for the sake of giving complete thing, because you know there will be a similar form for the conservation mass continuity equation in spherical form also, but I am not going there because it is way out of the purview of this course. Then we go to the this thing, uh, acceleration. So earlier we only defined its formula, but you know, uh, one second. Yeah. So next is acceleration. Here, what you do is acceleration is nothing but again like every other uh, quantity in the this discussion, it will also have xyz component in the Cartesian coordinate system, and here your ax will become u into one second. This part is also sometimes confusing, so I'll just explain in slightly detail. So it becomes del u by del t plus v dot gradient operator into u. Okay. So now what is this? If you expand, so it becomes like this: u into del u by del x plus v into del u by del y plus w into del u by del z. And similarly, ay becomes del u by del t plus this operator into v. Oh no, it's not del u, it's del v by del t, unsteady component, and and z acceleration will be del w by del z del t plus v dot u into w. So this is your local or temporal acceleration component, and this is your spatial or convective component. Okay, so and your like I've seen in many questions, what they do, they give some velocity field and they ask what is the acceleration at xyz point. That's it. So there you may get confused that are they asking for ax, ay, az? But if it is not clearly mentioned, then what they are typically asking is the magnitude of acceleration at that point, and it is vector sum, or maybe this is like this is az square. So this is what they are asking. Uh, Resultant, resultant of all these three things. So hmm, so like here I would like to mention one more thing. Uh, this acceleration is nothing but vector quantity. So vector quantity is defined by its magnitude as well as the direction. So what happens? Okay, before solving some example, we'll consider, let's say, this thing only. Uh, so let me make some space. Oh, nice. Yeah, so let's say you have a tank, or you have a tank, okay, like this. And this is the free level. Consider this as a horizontal line, okay? I'm just drawing for the, and this is your cross-sectional area 1. And this is your cross-sectional area 2. So, and this is your height. H. So, and fluid is flowing in this way. That is the outlet of the fluid flow. So now, if H is constant, we know velocity will be under root 2 gh, which is again constant, right? So in this case, between 1 and 2, the fluid flow that is taking place, uh, there is like like del v by del t will be 0, because it's a steady flow. Since the head is almost constant, velocity is constant, and it is not a function of time. So its change with respect to time is 0. And since it is a constant cross-sectional area pipe, area is constant. Therefore, with respect to space also, it is not uh, having any change. So del v by del s is the uh, you know with respect to space between 1 and 2, since it's a constant cross-sectional area pipe. So therefore, here if I use the
So do you get ds or not? Do you get ds is equal to 0?
yeah, 1 second. So this is the terminology that I'm using. So local acceleration component, I'm denoting it by AL, and spatial is by AS. So S is basically, let's say, any coordinate. So for the sake of ease, you can consider S is along this direction. So this is, I mean, it will be easy if I consider as X, but this is the general term, right? It can be X coordinate, Y coordinate, Z coordinate. It depends on your choice of the geometry, right? So here you consider S as the coordinate axis which is parallel to the fluid flow. So since there is no change in the area between the pipe, cross-sectional area between point 1 and 2, there will be no acceleration in the s direction also, right? I'll show you the third case, maybe there you'll understand it better. So this is the first case. So here there is no unsteady part, no non-uniformity. So in this case your AL will become 0 because of this, because there is no time derivative, and your AS becomes 0 because there is no non-uniformity in the flow also. But if you consider the next case, one second, I'll just copy this. So consider the case here. H is not constant. So your velocity head is continuously coming down as a function of time. So therefore, there will be change in the velocity with respect to time, right? So this will not be 0 now. But whatever is the velocity, between point 1 and 2, velocity is constant. So with respect to the s direction, there is no change in the velocity. So this will be the 0. So this flow is unsteady, but it is uniform, still uniform, because the cross-sectional area is constant. So in this case, maybe I should increase the height of these lines. Yeah. So in this case, your a local acceleration component will not be 0, but your spatial component will still be 0. And yeah, here it is a steady plus uniform flow. Now the third case, which is one second. So third case is something like this. So here you have, oh, one second. Here you have pipe cross sectional area which is decreasing. And this is the flow direction. So now here your head is constant, but area, cross sectional area at the outlet or the 2 point is smaller than the first point. So here what happens, since the head is constant, there is no unsteady part. So there del V by del T will go to 0. But del V by del S, which is the rate of change of velocity along the S direction, will be non-zero in this case, because the area is decreasing and therefore velocity in the S direction will increase, right? Because same mass is flowing through the point 1 and 2. So this is the case where it is steady plus non-uniform flow. And here what will happen? Since it's a steady, your AL will be 0, but AS will not be equal to 0. So this is how one must understand these things. Yeah, Praveen, you are asking something. Is it cleared or you still have the doubt?
No, clear, sir, clear.
Clear, right? One second. So, I mean, this is important thing, because if you understand this, you'll solve the problem. Problem solving is okay, it's important, but concept is also important. And there will be a fourth case when your head will also be changing and your pipe cross-sectional area will also be decreasing. So in that case, it is a non-steady, non-uniform flow. So both AL and AS will be non-zero in that case. So I'm not writing that because that is calculable from this discussion. So I hope this is clear. Then, yeah, maybe some questions if I can find. maybe what I'll do, I'll just finish what I want to discuss, and maybe we'll solve some questions in the end, because to find question only regarding the acceleration. Okay, 1 second. Yeah, maybe we'll solve these questions later. Let's go to the next part. Then there is something called as a like for a fluid domain, there is something called as translation, then something called as deformation, and something called as rotation. So as the name suggests, translation means it's pure function. Like if you have a square of like your area of interest is a square fluid domain, it will just simply be transferred from one coordinate xy to the x1 y1. There will not be change in the shape of that domain. For example, maybe I can draw one simple diagram. So maybe if you have a fluid domain, something like this, let's say A, B, C, D. So translation simply means, so at t equal to 0, it is here. So translation simply means uh, at, let's say, t equal to t dash, which is greater than 0, it will be simply same domain will be simply at some other point. So it will be somewhere like something like this. But the fluid domain shape doesn't change. It doesn't deform or anything. It's a pure translational case. And this happens when, so this is the case of, one second. This is the case of pure translation, or maybe translation I can write. So this is translation, and it happens when your u is not function of xy, or it's just a constant with respect to xy. But this should be the clear. So whatever xy, like we solved some problems earlier, right? So here your u was xy square, u was lambda xy cube minus x square y. So if you want pure translational motion, you will have your u and v constant with respect to xy, if it is a 2D domain, which is what we are studying here. And if it is rotational thing, so what will happen? Maybe I'll use some different color. So at t equal to t dash, if it is a rotation, what will happen? Can I copy this and paste? Copy, paste, but I want to turn it. Is it possible? Okay, no. Okay, delete. Paste image. Okay. Copy. Paste image. Nah, it's not paste. Anyway, what I mean by this is, if it's a pure rotation, let's say it is rotating clockwise, then what will happen? It will become something like this. Anyway, so it will become something like this. So your A point will maybe get shifted here, C will be here, D will be here, B. So don't like, please excuse my drawing skills here, but in pure rotation, there will not be any deformation in the shape. So it should be looking like this. Okay, and this happens. This is rotation. So everything got rotated clockwise. Rotation without deformation. Your original domain remains like this only. And this happens when your if u is function of y and v is function of x. So in that case, this thing happens. And then there is last case, which is called as maybe I'll use some other color. Yeah, so then there is third case, which is called as deformation. So as the name suggests, deformation can be like this domain will not remain as it is. It will get deformed into some other thing. So maybe I don't know, I mean, how to draw it, but 1 second. Yeah, so deformation, I mean, I think you get the idea. It can be angular deformation, or it can be just a linear deformation also. So what I mean by that is, if I just bring the point more clearly. So this was your original domain, right? So what can happen? It may get deformed like this. So then your this point is still A dash, B dash, C dash, D dash. So here the deformation is along the principal axis, which is x and y. But there can be another case also when your deformation can take place something like this. Yeah, so there can be a case when your deformation also takes place like this. So that is your angular deformation. So here also your A dash is same point, but C dash is here. Maybe I'll use double dash, C double dash, D double dash, B double dash. So what I'm trying to say is deformation can be angular or along the principal axis. So therefore it is uh, that's how you need to study it. So therefore there are uh, rate of deformation is defined in this concept. So typically it is epsilon is used for it, and since it's a rate of deformation, so it is typically having this type of structure: xy, xz, then this will become y, this will become yy, this will become yz, this is zx, zy, and zz. So the principal components, which are like, maybe I'll use the highlighter. these components are responsible for the like deformation without any angular component, and other components which are having x, y, y, z or different axis in their name, they are responsible for the angular deformation. So I'll just make a note here: not responsible for angular deformation. Maybe I'll write principal components, because these are the principal components of strain rate matrix, and other components are responsible for angular deformation. So this is just an introduction. Important term to remember here is uh, something called as volumetric strain. Which is nothing but summation of principal components. And if you have like there is a derivation to it, but we don't go through that now, but you should know this. This is equal to your divergence of velocity. So if this flow is incompressible, then this volumetric strain rate again becomes, if flow is incompressible, we have seen earlier that this means the velocity, divergence of velocity is 0. This implies volumetric strain rate is also 0. And for other components, see, I will give you an easy formula to remember. There is something called as vorticity, which is typically defined with this symbol, and it is it is basically the mathematical measure for you know quantifying the rotationality of the flow, and by definition it is curl of, one second, is it curl of velocity? Let me just confirm. Yeah, before going that, I forgot one point. And this volume flow rates, sorry, shear strain, other, so principal components, I said they are responsible for the uh, like this along the axis deformation, which is called as normal deformation also. And the other components, which are let's say for example epsilon yx, it will be nothing but half del v by del x plus del u by del y, and it will be same as epsilon xy. So you should remember that, and this comes from the geometry of it. Maybe in class they have told you, but like from geometry it comes, and therefore if you don't want to, if you don't know how to remember this, you just remember that you know principal components will have u with x, v with y, w with z, but this non-principal components of the strain matrix will have u with, u and x will not be together. That's it. That's how you remember. For example, if somebody asks me what will be epsilon yz, so what I can do, what I know it is yz, so there will be del v and del w. So this much I know because it is yz. but v will not be together with the y, so it will be with the z, and w will be with the y. So, and again, this is a symmetrical matrix, so this will be equal to zy. And you can go back and cross check. This is the correct way to do that. So, like instead of mugging up the formula, you can just remember the main thing, how it comes. And for the rotation last part, this thing, maybe I think today also will not have enough time. Anyway, for the rotation, as I said, there is something called as vorticity, which is like defined like this, symbol typically used for it. I just want to confirm its formula, 1 second. Yeah, so basically it is defined as curl of velocity. So again, in the vector notation, it will be something like this. Maybe we will not use the for like gradient or that operator. We are not using vector line, and your angular velocity vector which is by omega, is half of your vorticity. Vorticity is actually not a vector name. Anyway, so like that. So basically, coming back to the important thing which will help you in problem solving, uh, this omega will be matrix which comes out of, there will be dx, dy, dz, or maybe del, and here it will be u, p, w. That's it. You don't need to mug up any other formula now. So, and again, for everything it will be like there will be some x component, there will be some y component, there will be some z component. So you know the matrix operation, right? So wx will be nothing but the first thing. So it is basically half will be there. It will be w del y. 1 second. Yeah, it is not w del y. I made a mistake here. It is nothing but del y del x, del y del y, del y del z. So here it will be del w by del y minus del v by del z. So if you can go back and cross check, this will be the correct answer. I have seen many students, struggling to remember these things, but it is my request to you that don't remember these things because you will forget them anyway. But if you just remember the trick, you will be able to solve the problems. In y it becomes slightly tricky because there is a negative sign in between. So therefore it becomes del u by del z minus del w by del x. And wz again, like wx, it is straightforward, half into del w by del x minus del 1 second z, right? Oh, so it will be del v here, and it will be del u by del y. Yeah, so this is there. There is vorticity expression in polar coordinates also, but I think we'll leave it at this only because otherwise it will become too much. And then there is a last part, conceptually speaking, in this topic. Maybe after that we'll take some examples, which is called as the potential function and stream functions. So maybe I'm just skipping through these topics very fast, but we have limited time, so that is why. So first of all, stream function we can consider. Which is conventionally defined or denoted by psi symbol. Uh, First of all, it is uh, you know it is continuity. Basically, if the flow is satisfying continuity equation, then the stream function will exist. So therefore, this signifies continuity of mass, and then it is a scalar function. So basically, it is not a vector function, it is a scalar function, and it is a function of x, y, z and time. And the formula solving thing, uh, del psi by del x equal to minus u, and del psi by del y is equal to, oh, it is, sorry, ulta. Del psi by del x is v and this is minus u. How to remember this? Uh, Maybe you can follow this trick. It's not the standard thing, but this is your x, y, right? And this will be your u, v, minus u, minus v. So you just remember that you take counterclockwise direction. So here del psi by del x, so that will become v, because you are going from clockwise direction. So with respect to x, you go 90-degree clockwise, you get v, and here you go del psi by del y. So from y you go 90-degree, you get minus u. So therefore you get minus u. I mean, this is just a trick. Maybe you can find some better trick, but it's like that. And there is one more property for it. Uh, One second. Yeah, this is valid for both rotational and irrotational flow, but it is defined for 2D steady, and I think incompressible flow. Maybe 1 second. Uh, 1 second. Hmm. Yeah, I mean, both, like, these things are defined for steady flow, but this stream function is defined only for 2D steady flows. So I should not write, maybe z should not be here. 1 second, is it correct? Typically we take only 2D examples, therefore we don't consider the validity of 3D. Let me just check. Is stream function for 3D flow? Hmm. Yeah, I mean, I am wrong here. It should not be 2D. It is valid for 3D also. But typically we study mostly 2D problems. That's why I think I got confused. Anyway, but it is for steady flow. That is true. Maybe I had read somewhere it is like that only, but I don't know. Maybe I'm wrong. And yeah, it is defined for steady and incompressible flow. Okay, so for incompressible flow, we know that del u by del x plus del v by del y equal to 0, right? So if you put v and u from this del psi by del x and del psi by del y equations, what you get? Del square psi by del x square plus del square psi by del y square equal to 0. And this is called as the Laplace operator. So this is the important thing. So for any valid stream function, its Laplace will be 0. Then important thing is yeah, there is one more important thing. So
We'll do double derivations here. D square, delta del square, and del x square. So
yeah, so what about it? Oh, okay, wait. Okay. So here, sorry. So del u by del x plus del v by del y equal to 0 for incompressible flow. So here, oh yeah. So this will be del square psi by del x del y and del square psi by del x del y, and this comes out to be 0. Yeah, sorry for my mistake, but yeah, thank you for the pointing out. So yeah, but the key takeaway is the Laplace should be 0. And another finding relevant to the stream function is along a streamline, psi will be constant, which again means del like d psi will be 0. But this is important thing to remember. So for any streamline, we will have psi value which will be a constant, and it will not change along the streamline. And last but not
sir,
least,
something wrong above just this one, sir. It is the same thing. Del square psi, then dx delta x delta y. The denominator
yeah,
both are.
yeah. So okay, so yeah, so the takeaway is that psi will not change along a streamline as long as it remains on the same streamline. And
Uh,
last, yeah, any doubts?
Something wrong, sir. I think something is wrong, sir. Here, just above this equation, that double like the delta square psi. I think denominator are same for both the terms. Dx del x del y, and here also del x del y. So that becomes 0. Yes, that becomes 0. Yes, you're right, sir. Yes, yeah, okay. Got it, sir. Yeah.
Okay. So yeah, and the last thing is I think one question was asked in the assignment for also you also that uh, rate of discharge or volume flow rate per unit uh, I think it should be rate of discharge between uh, two streamlines is given by psi1 minus psi2, and this is like the mod sign is used here because volume flow rate is always positive. So in some cases If it comes negative, you have to take the magnitude which is positive. And yeah, then the last conceptual point is this one, which is called as the velocity potential functions. So this stream function we defined. Then there are like they are typically called as potential functions and denoted by phi symbol. Again, they are also scalar function and function of scalar function of x, y, z, and t. But this is, uh, this comes into picture to define the rotationality of the flow. So, like signifies rotationality. Right, I should just say rotationality of the flow. So its primary, the reason why it came into existence is to define the rotationality or irrotationality of the flow, and its value is typically, this is easy to remember because uh, del psi by del phi by del x is negative of u, and del phi by del y is negative of w, like that. So negative of v. So everywhere it will be negative of that respective uh, component. And again, it is also defined for steady compressible, steady and incompressible flow. One second. Yeah, for steady incompressible flow, again you go back and put this definition here and you will get mm, so u del u by del x, so it will be, one second, yeah, so it will become del square phi by del x square plus del square phi by del y square equal to 0. Here it will be x square because u is del psi by del x. So if I take derivative, it will be del square by del x square. There will be one negative sign, but since it's summation, it should be like multiplied with -1, doesn't matter. So here Laplace becomes 0 for the velocity potential function also. And uh, one second, I need to tell you something. Mm, uh, one second. Yeah. So if flow is irrotational, let's say wz is equal to 0. So this is your angular velocity across the like about the z-axis. So this, from the formula, this is del v by del x minus del u by, one second. So if you put here, this becomes del v by del x becomes uh, minus del square phi by del x del y, another term will become del square phi by del y del x, but it doesn't matter because and 0 is so that means if flow is irrotational, velocity potential will exist. So therefore, if the flow, like if you talk it in the reverse sense, if the flow is irrotational, then if the flow is rotational, then the velocity potential will not exist. That is how it is. Yeah. Therefore, one important, therefore phi will not exist in, some of the examples are within boundary layer, because there the viscosity effects are dominant and therefore the rotationality is induced, and sudden expansion or contraction or bend in pipes. So there also fluid becomes, because of these things, it gets rotational tendencies, and therefore it is, you cannot define uh, this thing, velocity potential function there. And last but not the least, phi and psi, if exist, will be perpendicular to each other always. They will be perpendicular to each other. Why? Because one second. Yeah. So
Sir, one question. So if phi is equal to 0, it will be rotational. That means
phi equal to 0.
it will be rotational.
One second. If you put phi equal to 0 in this question, then omega z becomes 0. Actually, phi equal to 0 is a trivial solution. Better
Sir,
answer will be, uh, you know, if phi equal to constant, then what happens? Then your u and v become 0. Yeah, and then your omega z becomes 0. So you can say if phi is constant along any potential line, there the flow will be irrotational because omega z becomes 0. Okay.
sir. So phi has to have a number to become irrotational. To become irrotational.
Yeah, because if there is zero velocity, then, like for example, if there is a particle with zero velocity, then you cannot say whether it's rotating or moving or standing, right? Zero is the trivial solution.
Got it, sir. Yeah. Got it.
Yeah. So like that. So okay, now I think, see, then there are some vortex motion, etc. topics are there, but I think we don't have time for that. Maybe one last thing in this is, uh, there is something called as Cauchy uh, Riemann equation. So basically, what they have done is, using some algebra, they have coupled these two things, del psi by del y equal to del minus del phi by del x, and del psi by del x becomes del phi by del y. It's just a maths. You can do that later. I just, because for the sake of completion, I have given this. Anyway, so now we can solve some problems. We have 15 minutes. 1 second. So now after this, I think problem solving should be not that difficult. I hope if you have understood these things. Yeah, so first question I'll take. Maybe I'll just put question. Yeah, so velocity field is given like this: x square y I cap plus 2x y square z into j cap minus y z cube into k cap, and it is asked that find this rate of shear deformation component of yz at point x equal to -2, y equal to -1, and z equal to 2. Okay, so now as we were discussing, we'll not go back to the formula because we can, like, based on the trick that I told you, we can write it here. So this is not the same axis. Okay, so there will be half outside since it's a different axis thing, and epsilon yz, so there will be y corresponds to v and z corresponds to w. But since these are off diagonal elements, they will not have the same thing, so they will have something like this. Okay, yeah, I think this is correct. I am not looking at the formula, I just remember the trick. So now we need to find del v by del z. So what is v here? V is minus y z cube, the v component of the velocity. So the derivation, the differentiation with respect to z will give you 3z square. So it is minus 3y z square. And del w by del y will be del by del y w. W is, sorry, I made a mistake. This is w, not v. So v is 2xy square z, and it will be 2xy square. W is minus y z cube, so it will become minus z cube. Therefore, epsilon yz will become half of del v by del z 2xy square, del w by del y is minus z cube. So now you need to put the coordinates. So typically you write the coordinates here. So this will be half into 2x is minus 2, y is minus 1 square, minus z is 2 cube. So this becomes half into minus 4 minus 8 minus 6. Yeah, so correct answer is minus 6 only. Then,
So there is a question in the chat box, sir. The last question of this. It is e to the power x, y, sir.
okay, 1 second, I'll see. In chat, huh?
Yeah.
Okay. Uh, For the velocity potential function e to the power x plus y, flow is this thing. Yeah, I think I saw this question. It's a tricky question. So again, we'll take this question. Your psi or phi is defined as e to the power x plus y. I think this is assignment question also. But anyway, uh,
Assignment last question, sir.
yeah. Then it is asked that the flow is, and you have multiple options. Let's say rotational, irrotational, and impossible. Okay, and fourth option is, let's say, none of the above. So here, see, first of all, before going to rotational, irrotational, you need to check whether this is a valid potential function or not. So that is checked by del square by psi del square phi equal to 0. And it is question of, if it is a question of stream functions, there also the first check that you do is Laplace, and then anything other than that. So here Laplace of phi, if you calculate, which is del square phi by del x square plus del square phi by del y square. So this is necessary condition for valid phi. So here for our phi, which is e to the power x plus y, what will be the del phi by del x? What will be the del phi by del x? It will be same, e to the power x plus y into 1, because like that. And same will come with respect to y also. It will be x plus y into 1. And if you take one more derivative, same thing. So it is x plus y plus e to the power x plus y. That is nothing but 2 e to the power x plus y. And it is not 0 for all x and y. Therefore, phi is not a valid potential function, and therefore the answer should be impossible. The flow is impossible. This should be the answer. Do you understand?
I
Pradeep?
perplexed a little bit, sir. Yeah, a little bit actually.
Yeah, so see, the point that I'm trying to make is, if any question like this comes now, whether this flow is rotational, irrotational, anything like that, the first thing you do is you calculate the Laplace, even for potential function or stream function, and that should be equal to 0. Then only you go to the next step. If it is coming 0, then okay, then the flow is valid, and then you can do the next part. We'll take one more question here so that you understand this. So, uh, 1 second. Yeah. Mm, Okay, we'll take in one question. The stream function is given as x square minus y square. Okay, and it is asked that find magnitude of velocity at point minus 1 1, or let's say 1 1. So now, first of all, I mean, in this question, so you need not to check, but just for the sake of our clarity, what is del psi by del x? It is 2x. Del psi by del y, it is minus 2y. And del square psi by del x square, it will become 2. And del square psi by del y square is minus 2. And therefore, del square psi del x square plus del square psi del y square is 2 minus 2, which is 0. This means Laplace of psi is 0, and therefore it is a valid stream function. So like that, you need to do the first check. If you don't do that and if you just start solving the question, sometimes they will catch you with this type of tricky questions, that e to the power x plus y. So anyway, coming back to this question, they want the magnitude of velocity at 0.11. So uh, okay, we know that del psi by del x is v and del psi by del y is minus u. Therefore, what is del psi by del x? We calculated. So v becomes 2x and del psi by del y is minus 2y. It becomes minus u. That means u is equal to 2y. Therefore, your velocity field is nothing but 2y into I cap plus 2x into j cap. And therefore, magnitude of velocity is nothing but 2y square plus 2x square. And here they are asking at point 1 comma 1. It becomes 2 square plus 2 square, which is square root of 8, which is 2 root 2. So this is the answer. And since it's a velocity, maybe you should write unit also. If I have not written it in the previous questions, you can understand that. It's okay. Okay. Any other question? Yeah. So this is quite interesting question. So what they have given is multiple choice question. Okay, more than one option correct in this. So they have given velocity field as x plus 2y plus 2 I cap plus 4 minus y into j cap, and it is multiple option correct. Okay, uh, possible matlab, like it is not impossible, it is possible flow. Second, compressible, and third option is rotational. So more than one option correct can be correct. So this is multiple choice question. So if you get such type of question, this is good for our revision because we have studied so many concepts. So here u is x plus 2y plus 2 and v is nothing but 4 minus y. So first of all, just to check if it is a possible flow or not, we can check the mass continuity. So what is the mass continuity? Del u by del x by del v by del y equal to 0, right? One second. No, this is for incompressibility, right? One second. Yeah, this is for incompressibility. One second. I am actually contradicting my own teaching. First, you can check the validity of Laplace of psi. If that comes to 0, that means it is a valid function. One second. Yeah, so here, again, del psi by del x is v and del psi by del y is minus u. So here, what is your v? 4 minus y, and del psi by del y is minus of u. So minus of x plus 2y plus 2. Del square psi by del x square 0 because there is no x there. and del square psi by del y square. It is minus 2. Okay. Hmm. So here your Laplace becomes summation of these two terms, which is minus 2, which is not equal to 0. And if this is not equal to 0, what does that mean? I told you, right? Where is that psi?
It is compressible, sir. Not it is compressible.
Yeah, so that means it is compressible, right? But one second. In the del u by del x, del v by del y. One second. Something is wrong. Is it from my side or? Hmm. Am I doing any mistake? Because the answer says the flow should be irrotational or incompressible. One second. Yeah, maybe we'll stop after this because we are already out of time. X plus 2y plus 2 plus 4 minus 5j. So del psi by del x is v, del psi by del y is minus u. Del square by 0 square y minus 2. It should be incompressible, right? Oh, sorry, compressible. What about phi?
It is. I think this is 0 probably. The double del square del y square. The integrate the derivation maybe should be instead of minus 2 should be 0 probably. Or
Wait, we'll check the. See.
del square this thing del square phi that del y square is equal to minus 2. I think it should be 0 probably.
But y is there, no? This y is there. How can I make it 0?
But oh, right, okay. But is it double, sir? Double y square it is 2 times.
Mm, okay, so one check that we can do for compressible or not is del u by del x plus del v by del y equal to 0, right? From earlier
Yes.
question.
Yeah.
So what is del u by del x? It is del by del x of x plus 2y plus 2. And what is del v by del y? Y is 4 minus y. So this becomes, first term becomes 1 and second term becomes minus 1. So 0. So therefore it is incompressible. Okay, just hold on. I think I understood what is wrong with this. And okay, so incompressible. That is correct. This has to be correct. Let's check the rotationality wala thing. What is the omega z formula? One second, I think it is del u by del z minus del w by del x. Okay. No, it should not be W, right? It should be del V. Sorry, we have the formula here, right? WZ wala. Yeah, so WZ is half del V del X minus del U by del Y. Del V del X. Del V del X minus del U by del Y. So what it is, half del V by del X. So del V by del X of V. V is 4 minus Y plus del by del X, minus del by del X of U. U is X plus 2Y plus 2. So now it is half. This becomes 0 minus 1. This becomes minus 1 by 2, which is not equal to 0. Therefore, this is rotational flow. Yeah, I understood. Uh, uh, so yeah, maybe this is actually good thing that came out. So it is a rotational flow and incompressible flow, and since it satisfies this is not equal to 0, right? So uh, like I told you, right, this note is psi is defined for rotational as well as irrotational flows. Okay, and therefore there are two cases. So uh, if Laplace is 0, that means the flow should be irrotational, and if Laplace is not 0, that means the flow should be rotational. So that is correct only, right? Because our Laplace square is becoming non-zero, and when we check the angular velocity Wz, that is also saying it is rotational. So therefore this all makes sense. So it is incompressible flow. So this option is not correct. So this is not correct. It is rotational flow, and it is possible also because maybe we can check the phi thing also. But since it is rotational flow, del square phi, since omega z is not equal to 0, I think phi, will the phi exist for this function is my question. 1 second. Okay, we'll check the phi, and oh, it's already 8:10. Huh? Okay, I'll just quickly see what happens to phi. Del phi by del x is equal to minus u, and del phi by del y is equal to minus v. This is the formula. What is minus u? X plus 2y plus 2, and del phi by del y is minus 4 minus y. So del square phi by del x square, it becomes minus 1, and del square phi by del y square, it becomes minus of minus 1. So it becomes 1. Del square, oh my god. Hmm. No, but 1 second. Yeah, phi is defined for irrotational flows, right? Here it is satisfying. Hmm. second. Let me think about this. If I am doing any mistake or something. Yeah, it is 0 only, but I think it's actually we are complicating things. Let it be this way because uh, see this part too I clarified, and since this is rotational flow, phi will not exist because phi exists only for irrotational flows. So del square phi equal to 0, it can be 0, it cannot be 0. We can't conclude their way. So that is actually adding confusion to the thing. And yeah, so this is, since it satisfies uh, this thing, what do you call? Now I just want to verify whether it's a possible flow or not. So can there be a incompressible rotational flow? Yeah, it can be there, right? In case of boundary layer, it is incompressible but rotational. So such flow is possible. So the first option is also possible. So like that we have to see. So this is the important note that you should be considering. So if like Laplace becomes 0, that means it is uh, Laplace of phi becomes 0, that means it is
Irrotational.
yeah, irrotational, as well as then you have to check incompressibility, like that. Okay, so we'll stop now because it's already 8:13.
Yes.
Okay.
Good night, sir.
Okay, good night. Bye bye. We'll meet next time. Bye.
Yeah. Thank you, sir. Thank you so much.